Now we're going to look together at experiments versus observational studies. So here goes. First, kind of an outline. We want to look at association versus causation. What's the difference between an observational study versus an experiment? And how do we conduct a randomized experiment? Okay. Explanatory, response, and causation. We want to identify for the following the explanatory variable and the response, and think, does it imply a causal association? Does daily exercise improve mental performance? If you think of this sentence, they're trying to use daily exercise to explain the response, mental performance. So daily exercise is what you're manipulating, so that's the explanatory variable, and the response would be mental performance. Want to lose weight? Eat more fiber. So in this case, what are they using to explain a response? Think about it. It's whether the fiber causes you to lose weight. So the explanatory variable would be kind of like fiber status. Did you have fiber or not? And the response would be, did you lose weight? Cat owners tend to be more educated than dog owners. Okay, I own a dog, so I kind of find this appalling. But in my eyes, I'm thinking they're using which pet you own to explain the response, how educated you are. So animal that you own would be the explanatory variable, and the response would be how educated you are. So the question becomes, well, even if we see some sort of association, does it mean that there's any causation? So two variables are associated if the values of one variable tend to be related to the values of the other variable. They're causally associated if changing one value of the explanatory variable influences the value of the response. I'll show you a couple of examples. This is a graph of TVs per 1,000 versus life expectancy in several countries. You can notice here there's a pretty strong positive linear association between TVs per 1,000 and life expectancy. Does this mean that we should go to poor, impoverished third world nations and buy them lots of TVs? Does the association mean that there's causation? No, because there's a lurking variable, a third variable, that causes there to be a higher life expectancy when there's more TVs. Do you know what that is? If you're thinking affluence, that's exactly it. Affluence is like a third variable, sometimes called lurking or confounding variable, that's driving this association. So even though they're highly associated, one does not cause the other. So should you buy more TVs to live longer? No. And there goes, association does not mean causation. So this third variable, this video is calling that I've looked at confounding variable, and AP Stats will call it a lurking variable, but it's really highly associated with both the explanatory and the response variable, looking like there's some sort of association between the two. A confounding variable can often be a plausible explanation for an association between the explanatory and response variable. So I want to just look here. You have your explanatory variable, your response variable, and a confounding variable. And the question is, do you have causation? For example, an explanatory variable might be sending more and more firemen to a fire. And the response might be the dollar damage. And they're highly associated. But there's a confounding variable. Yep, fire intensity. The more intense the fire, the more firemen are sent, and also the more damage the fire will do. Like TVs and life expectancy, wealth is our third variable that's driving the association between the two. One of my favorites to think about is that more ice cream sales have been linked to more deaths by drowning. Again, the explanatory is ice cream sales. The response is deaths or number of deaths by drowning. You tell me, what is the confounding variable here? So an observational study is a study in which the researcher does not actively control the value of any variable. He just sits around and he watches. An experiment is a study in which the researcher actively controls one or more of the explanatory variables. I'm going to say this very slowly. In my book, an experiment becomes an experiment when you randomly impose treatments. In an observational study, you're watching and seeing what people do. For example, you might observe that people who smoke were more likely to get cancer. But we don't randomly assign people to smoke. Maybe there's some other reason that those people who chose to smoke do get cancer. An experiment, the treatments are actively imposed through a random assignment. That is key. So, in an observational study, there's always going to be confounding variables, and you can pretty much almost never use them to get causation. Got it? I think you got it now. Now, randomization can help us avoid confounding variables. If we randomly assign values of the explanatory variable, we have an experiment. So in a randomized experiment, the explanatory variable for each unit is determined randomly before the response is measured. For example, I might be doing an experiment to see if flossing leads to less cavities. So I would randomly allocate some people to floss and some people to not floss. If I didn't randomly allocate and I let people self-choose, there's a really good probability that the people who floss are healthier eaters to begin with, and that they'll have less cavities because they're healthier eaters. Randomizing eliminates this confounding variable. So in a randomized experiment, the explanatory variable for each unit is determined randomly before the response is measured. Now, many times there are different levels of a treatment. For example, I might be doing an experiment and I want to see if a new depression medicine works. So I might use a full dose, a half dose, and maybe I'll choose to have no dose to see what happens if there's no treatment. We would randomly divide the units into the groups and then randomly assign the treatments to each group. If the treatments are randomly assigned, the treatment group should all look similar. If a randomized experiment yields a significant association between the two variables, we can say that causation exists. So association might not mean causation, but if you do a randomized experiment, you can get causation. Randomized experiments are very powerful. They allow you to infer causality. I'd imagine this is one of the major things that the exam in June will want you to know, is that causation can only be shown with an experiment. So it says a study found that elderly people who walked at least a mile a day had significantly higher brain volume and significantly lower rates of Alzheimer and dementia compared to those who walked less. The article states walking about a mile a day can increase the size of your gray matter and greatly reduce the chance of getting Alzheimer's disease. Is this a valid conclusion? Well, I'm going to ask you, was this an experiment? Nope. It's an observational study. It cannot yield causal conclusions. But we could run an experiment. We could think, how can we design this experiment? Well, maybe we take a group of mice and we randomly allocate them into two groups. One is given access to an exercise wheel and the other is kept sedentary. The brains of mice and rats were then allowed to run on the wheels with vigorous, newly born neurons, and those animals then breezed through the mazes and other tests. Can we now say causation? Yes. We randomly allocated the mice to the treatment, so we now have causation. How to randomize? Well, we could do what we did with the simple random sample, put all the names in a hat, shake the hat, and the first half go into one treatment group, the other half go into another. Or we could put all the subjects' names on cards, shuffle them, and deal them into piles for however many treatments there are. Or we could use some sort of technology, for example, assigning random digits and letting our calculator pick digits, and the first ones it picks go into a certain treatment group. Let's try it. No, we're not going to try it. Let's skip this part and go to knee surgery for arthritis. Researchers conducted a study on the effectiveness of knee surgery to cure arthritis. It was randomly determined whether people got the knee surgery. See the random assignment of the treatment. That makes this an experiment. Everyone who underwent the surgery reported feeling less pain. Is this evidence the surgery causes a decrease in pain? No. We randomly allocated, but maybe the people would have been feeling better anyway over time. We have no group to compare them to. So it would be really nice if we had a control group. So when determining whether a treatment is effective, it's important to have a comparison group known as a control group. It isn't enough to know that everyone improved, because they might have improved anyway. So all randomized experiments need either a control group or, if not a control group, different treatments to compare. So let's relook at this. In the knee surgery, those in the control group received a fake knee surgery. Ouch! They were put under and cut open, but the doctor did not actually perform the surgery. All of these patients also reported less pain. Wow, in fact, the improvement was indistinguishable between those receiving the real surgery and those receiving the fake surgery. Oh, wow. So even though they had the treatment, there was no noticeable difference. So sometimes the people who get the treatment think they're better, and that's what we call the placebo effect. Often people will experience the effect they think they should be experiencing, even if they aren't actually receiving the treatment. So I'm just going to point out here that one study estimated that 75% of the effectiveness of antidepressant medication is due to the placebo effect, meaning the people who had the placebo felt just as well as many times the people who took the antidepressants. Placebo is a form of blinding. Blinding means that you don't know which treatment you've gotten. So a placebo is a fake treatment that resembles the active treatment. It's helpful for participants to not know whether they're getting the placebo or the active treatment. Now, keyword, I just kind of lost that here, is double blind. An experiment is double blinded if neither the participant or the evaluators looking at the results don't know which treatment the person had. So if I were in some sort of experimental group for some new medicine, I wouldn't know which medicine I was getting, and also the people evaluating me wouldn't know. Okay, I'm going to skip a little bit ahead because I'm running out of time. I have a 15-minute limit on these videos, but we're going to kind of look here and summarize. If your sample's randomly selected, you can generalize to the population, if not only to your sample. In an experiment, most times people are not randomly selected to be in the experiment, they're volunteers. So a lot of times we can't generalize to everyone. But when the explanatory variable is randomly assigned, meaning the treatment, then we can make conclusions about causality. If not, we can't. So one major issue with experiments is that although we randomly assign treatment, which means we can get cause and effect, if our subjects weren't randomly selected, then we can't generalize really beyond our subjects or people very similar to them. I threw a lot of vocabulary at you, and I hope this helps. See you soon.